Okay, welcome to the afternoon session of the second day. It's my pleasure to introduce Eleonore Faber, who will be telling us about non-commutative resolutions of normal toric varieties and beyond.
Thank you very much. So thank you very much also for the invitation to this wonderful conference, and thanks to Karen. That's the most thing. So maybe I should say a few words how I got to know Karen. Like I think the first time we met was in 2011 in Lumini, where Karen gave a wonderful series of lectures on test ideals and FQ thresholds. And so actually this became a paper which was published in the 65th birthday volume for David Eisenbach. So it was a theme. And so what I'll be talking about is actually joint work with Bergh, Muller, which is in the audience, and Karen. And this was done later than 2011. This was done when I was a postdoc with Karen in Michigan. And that was after I spent a semester at MSRI, where I was in the commutative algebra program. And at the same time, there was the non-commutative algebra representation theory program. And I somehow got into the dark side of things, which are these non-commutative resolutions. And so, yeah.
Commutative algebra.
They are,
absolutely.
Still, yeah, they're a little bit representation theory, I think. Okay, and so we'll talk about that, and then probably also, since the title says "and beyond," that is in progress, showing work very much in progress with Milena having Sure. So I want to start with some motivation because why do we care about endomorphism rings, about non-commutative rings? And after that, I'll say a little bit about our theorem. So following Karen, I will state the theorem and then maybe say a little bit about the proof. And then the non-normal stuff, if there is some time. And so first, what is the setting? So always X is a affine variety, so it's a spec of the ring R. It's an affine variety. And so far, everything is commutative. So R is a commutative ring, Noetherian. And so we have already heard several talks about this, but if you want to study the singularities of X, there's like various ways to do that. And one thing that Czech was telling us about is the ring of differential operators. So this is a variety over field K. So far, my field K is also anything. And so we can look at the ring of differential operators. That thankfully Czech also defined yesterday, so I don't have to do that anymore. But so this is with the Czech's definition, but also I want to repeat the most basic example is if we take K is equal to C, and then R is the polynomial ring in one variable, then Cx, then with DKR is the Weil algebra, and so this is still sufficiently nice, as you probably remember from yesterday's talk. And in particular, this is like it's a non-commutative ring, it's Noetherian, it's simple. It's relatively nice. And then in characteristic P, we have seen that this DKR is not as nice in general. So the characteristic of K is 0, and DKR is, so again, if R is the polynomial ring, so this is X is already non-Noetherian, so it's not a finite degenerate algebra over K, and but it's still simple. So, but still simple. And yeah, we already heard the theorem there proved by Karen and Michel, that if you have a field of characteristic P and your ring is strongly F regular and a finite F representation type plus some grading, then this DKR is simple. So it's a good non-commutative ring. Well, then you might ask like about other properties of this DKR. So you could look at as DKR, like is this like a smooth ring in some sense? And one thing to measure like how singular DKR itself is to study the global dimension. So study how singular DKR is, what is it? So for those who don't know what global dimension is, so this is just the supremum of the projective dimensions of any module over DKR. So this is also like in the commutative case, it's very well known what this global dimension is, namely, so well known. So for any our commutative global dimension of R is finite if and only if R is regular. So in the commutative case, so this is booked from Alpha first one. There. So in the commutative thing, in the commutative world, so this global dimension basically just tells us is the ring regular or not. But in the non-commutative world, this global dimension can be like much more nuanced. And it can also have like different values, because here, if you have finite global dimension, it will always be like the cruel dimension of the ring. And so for DKR, of course, we're looking at the first example, namely of the polynomial ring. So what is known there is, so for R, a little differently, so that can be rows and J's is 0 and ultimate for the P ratios if R is regular, then it follows that the global dimension of DKR is actually equal to the full dimension of R, and that is finite. Of course, I start with a regular finite ring of finite full dimension. What is interesting about this theorem is that, so it was proven by 3 different people, and so this, what the characteristic 0 proof essentially is like a variation of like, yeah, you localize and get something that looks like a polynomial ring, so you have the Weil algebra, you know that this has finite global dimension. But then the characteristic P proof is like very different. So it uses some techniques from Auslander about like in general like a bounding global dimension of rings. And so, well, then you might ask the question, well, we know for regular rings, we have that this ring of differential operators has finite global dimension. So what's you? Are there any other examples of rings with global dimension? They are finite. I mean, this could be a characterization, but well, spoiler is it is not. So toric rings and characteristic P are counterexamples, or like are other examples. So there are indeed non-regular rings where this has finite global dimension. So this was kind of the like guiding question in some sense.
But in that case, is it equals to dimension R also?
Yes, or do you mean for the
the converse?
I'll come to that. So, the answer is we don't know. But yeah, there's more about this. And so this is the differential operators, but the title of my talk that I just erased was non-commutative resolutions. So non-commutative resolutions are certain endomorphism rings.
So Eleonore, so is there any in the characteristic P setting? Is there any hypothesis on like essentially finite type monoid?
Finite.
Yeah.
Here, you mean for the Paulson's result? I don't remember.
So what I mean is that you can look at the differential operators on maybe if P or if P are joined one variable, and it will be two different.
Yeah,
it needs to be F finite.
Yeah, it probably needs some more. So, but I really don't remember what the actual assumptions there were. Well, if we stay with that, how do we get to this endomorphism rings? So in characteristic P, if we look at this DKR, we can write this as a direct limit of endomorphism rings of R to the E to the E R, and this is the same as saying as and R to 1 over P to the E. So it's like a direct limit of endomorphism rings. So here endomorphism rings first appear. And so if we want to know something about the global dimension here, so maybe if we first understand what is the global dimension of these endomorphism rings, well, we should be able to say something about the global dimension of this whole thing, which is the direct limit. So that's the idea why we get to the endomorphism rings. And so we're just like studying endomorphism rings. And these endomorphism rings, they're like interesting because if the endomorphism rings of the forms of N or M, where M is a finitely generated module, are interesting for so-called NCRs. So NCR stands for non-commutative resolutions of singularities. And so I don't want to say too much why they are called non-commutative resolutions of singularities, but what you want is, you want that the global dimension of this endomorphism ring and Rm is finite, plus some extra assumptions. And that's what's called a non-commutative resolutions. In particular, one of the extra assumptions is that M is, well, depending on which setting you are, it's either reflexive or just finitely generated or faithful. And so this non-commutative resolutions, so these are essentially endomorphism rings of finite global dimension. And here I should maybe also mention that so this non-commutative, there also exists non-commutative Krappen resolutions. So, commutative Krappen resolutions and CCRs that are due to Bergh. And those were the ones that were like first studied, because they are really some non-commutative analog of a crescent resolution of singularities for some like, from a birational geometry point of view. And yeah, if you want, so as I said, I don't want to dwell on why these are called non-commutative resolutions, but there are some nice surveys on this. So, surveys. And ours is one that's especially nice for commutative algebras. Bergh from already 2012, and then there is various on NCCRs. In particular, there is one there are two from Michael Williams, and also from the most recent one, I think, is from Michel from 2022, and Williams has one from 21 and 2019, I think. So there's a lot of work on this. And so I just want to say here, this non-commutative resolutions in general are like, an active topic of study, and there's like various examples. So there is like just to give you a few ideas, like so in Bergh's original paper, where like invariant rings by finite groups have like a non-commutative crescent resolution, and also some three-dimensional rings. And then there is also work that I will from Spenko and Michel that will appear a bit later. And very recently, actually, there is a toric thing by a lot of people, by Bergh, Bergh, and I just write here some dots because there are like 9 authors to this paper, which, so this is from 2025, which do non-commutative resolutions for normal toric varieties. So I should have said we're doing affine toric varieties, so they're doing the general case, and this is a very nice paper that constructs non-commutative resolutions in general. So,
Or is it a generalization of what we do, or is it different?
that is a good question. So they use, I think essentially it's I would say it's similar, but of course, so basically they're using a lot of techniques from this Hanlon, Pixla, Sarah paper and mirror symmetry. But I think in the end it comes all down to the same like type of resolution of the conic complexes that we were also considering. But of course they have like more machinery. Okay. So then the second part is now, so this was all the motivation part, why we want to care about endomorphism rings of this R to the 1 over P to the E, and also like for this differential operators. And so now what did we actually prove? So this is a paper 2019. So we're looking at ring Kx, the coordinate ring and phi. variety. Then we have the following. So 3 things. So there exists a reflective, and it's not even only reflective, it's even maximal combinatorial if you prefer that. Finally generated arbitrary A, like what called A, such that morphism over this A has global dimension equal to the dimension of R. And here, so this K here, this is completely arbitrary, so nothing characteristic B, this is characteristic 0 as well. So this just is we have a non-commutative resolution. Then the second result is, so I'll also tell you what this A is. So this is not quite the R to the 1 over P to the E, but close to it. The second part is, so now in characteristic B, so in characteristic 0, we have that BKR has finite global dimension, and in particular, we have a bound on this, but no equality, so it's bounded by the dimension of R plus 1. So it can't be too big. And the third one, although I didn't define it, but so the ring in A is CCR, so that's a particularly nice non-commutative resolution, if and only if the toric variety X is simplicial. This just for toric variety, we always have like a cone associated to it. That simplicial means that this cone is precisely a number of minimal generators is exactly the dimension of the variety. And yeah, the non-commutative preference resolution. This means for non-commutative resolution that I only said. So the main result, the main property we need is that the global dimension is finite. And here, what you want extra for in CCR is that also this ring here is what's called homologically homogeneous, which means that all the simples have the same projective dimension. Or you can also show it's equivalent to saying that this NRA itself is the maximal conic model over R. But so this is the theorem. So far so good. Yes.
When is the equality? Or I think greater than equal, that means it is achieved, I guess.
This one.
Yes.
Yeah, so as I said, we don't know. So we just have the inequality. So this is like the remark where this is coming from. So first for the first part, so we weren't the first ones to prove that. This was first proved. So one was proven by Spenko and Bergh in 2017. So they actually proved existence of non-commutative resolutions for quotients by reductive proofs, but with like a very general machinery, which also worked for like different examples, not only the toric ones. But what they didn't do, they didn't like determine what exactly the global dimensions of these rings are. So, but with global dimension equal to the Crow dimension.
Then I should say that our methods are not good enough to use actually.
Are they not? So yeah, so I mean, yeah, but on the other hand, you can do much broader scope. But I mean, I'll tell you more about this. But I mean, our method is really like tailored to the toric case.
So what is A in that case, like in the reductive group quotient case?
It's the same as or well, it's like coming from these modules of covariance.
Is it coming? Are those the summations of the push forward, covariance push forward again, or?
You mean for reductive? So I think your paper is a characteristic 0, right?
Yes, but yeah.
Yeah.
No, it's not known for reductive groups that you can do it with Frobenius push forward. We have one series of examples, but no.
Yeah. So yeah, that's that one. Then the second thing, like what is this mysterious A here? So this A, this is actually something that is yeah, it's like a reduction. So end RA is Morita equivalent to end R of the Frobenius push forward. So it basically says that like so this R to the Frobenius push forward has like a lot of different direct summands, as you all know with like you know something about F signature and stuff. But what we take is this A is just like we take one of each of the direct summands, and this is our A. And for determining the global dimension, it's enough if you look at the like reduced module here. And then the third remark here is that this 2 with this inequality. So why do we get an inequality here? This follows from a very general result of Bergh. Namely about the global dimension of direct limiter rings. And so it says that the global dimension of the direct limit of these endomorphism rings is just bounded over to the E is bounded above by the lim sub of global dimension. I always have like global dimension of n r to the 1 over p to the e plus 1, but there's a plus 1 at the end. So this is where this is coming from. And so we weren't able to actually show that it's equal to. So we can show like each of this has like has global dimension equal to the Kroll dimension, but we cannot get rid of that plus 1. So for this, I think you would need to know, like, to look at these endomorphism rings, and then what, like the bigger ones have to be flat modules over the smaller ones. I think that was the missing piece, which, yeah, I'm not sure if it's true or not. So if somebody wants prove something or disprove, have a look at this. So this is the theorem I want you to remember from the talk. So, the main theorem, but also interesting is how do you prove this? So the proof of this, so now I'm talking about 1, the proof of 1 that uses so-called conic modules and conic complexes. Yeah, this is really toric toric geometry, and this also, as I said, okay, has any characteristic. And so for this, I need to like go into more what actually is a affine toric variety. If I have an affine toric variety, a normal affine toric variety, I can always write it as a algebra generated, like the generators are monomials. And so this here is the lattice M. This is some d to the d, and we call this is like a cone. So this is a pointed. What else do we need? Rational, polyhedral cone. It lives in the vector space MR. So this is just a tensor M with R. And yeah, if some toric people are here, that's usually in the literature. This is the sigma dual. And so this is, you can also write this as the span of monomials x1 to the alpha 1, x2 to the alpha d, where alpha is in C intersected M. And so the typical example that is not the polynomial ring, so if I have M in 2 and C is just the ring, the cone generated by E1 and E1 plus 2 E2, then the lattice M, and then the cone C, and if you look which monomials do I hit? So in this case, example, in this case I get K intersected M, that's just K, so I'm hitting X, Y, and X squared, and you can see that this is actually isomorphic to the coordinate ring of a cone. And this is of course a normal ring. Then, so these are the rings that are these coordinate rings of toric varieties. Then the next thing is, how can we describe this Frobenius push forward? This is also, I think this was already mentioned. So this R to the, so I'm writing e to the e as q. So R to the 1 over q is then given as ring K C intersected 1 over q M. So just like make my lattice smaller and see which monomials do I hit. And it was, I think, first shown by already several times cited paper, Smith and Bergh, that this part the 1 over q is a direct sum of rank 1 modules, and yeah, of what's called finite F representation. So this R is a finite F representation type, meaning that only like finitely many isomorphism classes of modules appear if like the Q grows. So R, yeah, R is RT, and then you can like also describe what these modules are. And I think this is at least in the book of Bruns to the left. This R to the 1 over Q is a direct sum of so-called conic modules. So yeah, I'll write isomorphism classes over V over Q. Percentages of these modules. And so what are these things? So these are called so-called conic modules. These are conic modules. Here. And the conic modules is because you can get all of these rank 1 direct summons of R to the 1 over Q. If you just move your cone around and look which of the monomials in the lattice are hit by that. And so in the example, so if we put our cone in any of the lattice points, and we will always hit like the same monomials with like some translation, but it will always have the same structure. But if, for example, we move our cone by like a half, so I put my cone here, then I'm starting to hit this one, so I get different monomials that are in here. Yeah?
Sorry, what is the sum over? I just can't quite read the.
So it's like, it's equivalent classes of this like quotient lattice.
What is the quotient lattice of? Do you read that out loud?
So it's Q inverse 1 over Q M mod M.
Wait, are those sigma over?
U's or V's over
Oh,
P.
these are V's. These are V's.
Oh.
There's no sigma here. So these are just like
V over Q, yeah.
V over Q. Okay, thank you.
So basically I'm taking a, so this would be, for example, my V over Q. This is just a point in the M in MR, and I'll move my cone around. And so these conic modules, they're all of the form, so you can actually write them. So each of them is of the form A V, where span CVM, where M is then lattice intersected plus V. So they're all of this form. So that's just like there's like just some compact way to write this. And so this finite F representation type means if I let the Q grow, then I'll always have the same direct summons, but they just appear with higher and higher multiplicities. And
Wait, so sorry, the AVs are the same as the R.
so these representatives, they're all of this form.
Right, so that's like with the. Okay, so the bracket R to 1 over Q subscript V over Q. That guy is the same as the AV.
Yes. I mean, yeah, you can choose your V. Yeah, I mean, this is bad notation. I'm sorry. Maybe I should call this like U or something, so it's not the same. So maybe this is called from like W. So this is like just W. It's any point in M R. So what I do is I choose any point, like for example, I choose my W here. Then I'll put the cone here, C, and then I look which monomials are in there. That gives the span of these monomials gives me a module over R, and then this will be isomorphic to one of these.
And what's the subscript then? Like after? Are you inverting something? Or what's going on?
This is the
Oh, that's the
quotient.
degree.
Yeah, so this is just a Q.
1 over QM, she just wrote QM.
No,
Yeah, so
but
I should just write 1 over Q, sorry.
No, it's not. This part.
Like the equivalent to class. She's just picking representative ones.
So it's like everything of degree V over Q plus something in M.
This is a degree shift or something.
Yeah, it's like these are homogeneous components.
Okay.
But the grading is like 1 over Q Just in the
But it's a
bonus.
graded piece.
Yeah, exactly.
Okay, so, sorry.
Sorry.
Okay, so,
I hate to do this to you, but, so, the statement is for any W in MR, there will be some V over Q in.
so for
the
any
sum-
W, you can look at the span, you will get a module, and there will be one of these that is isomorphic to this AB, that's the statement. And you can even say much more about this, so what you get is then that, yeah, if you let the Q grow, then at some point you won't get any new representatives. So this R 1 over Q, this is just like off the form, where you have like, yeah, some of these direct, some of these ABs, and then they just like, so this is, yeah, it's very imprecise. Okay. And then what I already said, the module we are looking at, so we're not looking at the endomorphism ring over this R to the 1 over Q, but then at the end, A, where A is a direct sum over the AB. So what I do is I'll take like one from each representative of these ABs, and that is the module.
That's a finite sum.
Yes, it's a finite sum. That's like a finite FFRT property. And so now, okay, so we're just studying this endomorphism ring. And so now, how do you get the global dimension of this thing? Well, one thing, the global dimension of a finitely generated algebra over R can make your life much easier than compute the projective dimension of all possible modules. You can just compute this as the supremum of the projective dimensions of the simple. So I'm now indexing with the V, which is this very bad. So projective dimension of SV, so where SV is graded in A module. So meaning for each direct element, I have a projective module and also a graded simple. And so I have finitely many simples where I have to compute the projective dimension. And so this is all over this like non-commutative ring here. And so you can compute this. So you can even write down what these are. So SC, they are of the form are a B modulo the radical B. And so this is for each of these conic modules. And so now, like, how do you get this? And so this is where the so-called conic complexes come into the game. So this is so construct a minimal projective, or first construct a so-called conic complex for each AB. And so this is a complex of these conic modules over your commutative ring. And then the idea is that if you let home into A into A B, this is a minimal projective resolution of SV. So this is the idea. So first, you know exactly that like your simples correspond to the direct sums of A to all of these conic modules. then you construct a so-called conic complex, and that gives you a projected resolution over the endomorphism ring. And so basically we are constructing so we are constructing a projected resolution over this non-commutative ring, but what we are actually looking at is like modules over the commutative ring. And oops, I'm already a lot behind from what I wanted to do, so how far I can get here. So for constructing this conic complexes, so we may shorten this. So we may partition R into so-called chambers of constancy. Namely, where we have that AV is chambers of constancy of delta. So AV is equal to A delta, where delta is the region in MR, AV is equal to AW. So what do? I look. So I erased the example. But so if you have like your cone, and if you only like move your cone for a little bit, then your module will stay the same. But then you can look at all the points where your module is the same, and this is what's like this chamber of constancy. So this really means like it's the same module, not only isomorphic, but the same one. And then you can get a partition of this MR, and actually what these parts are, so partition into chambers of constancy, and so these COCs are locally closed disjoint zero regions, and this gives you a CW complex or CW decomposition. I'll do it in the example. So in the example, so we have just to remind you the cone. So this one here, and so if I'm looking now, if I'm at this point, then I'll see like I can move like quite a bit, and my module will stay the same. So I'm not hitting any. So you can move a little bit to the left, and my module will stay will stay the same. But if I just move a little bit to the right, then I won't hit this point, and I will get a different module. And so in this example, so here, over the cone, two possible a deltas. So one is the ring itself, and the other one is where I just take XR1 and XR plus XYR, so it's R plus YR, A2. And so now we can draw a fundamental domain. Here, possible isomorphism classes of AVs are these two. And So, fundamental domain is the following. So this is always the square. I'll draw it a little bit bigger. Is 1 minus 1. So this here is 0, 0, minus 1, 0, minus 1. And then if I'm here red, this region here, then so if I choose the V in this red region, then I will get something that is really equal to R. And then in the yellow region, I will get something that is equal to this one here. And here. This and yellow again. And so you can now plaster the whole plane with this, and you get some kind of checkerboard decomposition of the plane. But what's important here is that these are like locally closed. So yeah, this belongs all to the chamber of constancy, but two sides are already in the yellow part. And then yeah, maybe I'll just do the complex. So now if I write the K delta, so this would be, so this here is a, yeah, so it's delta 1, and here, or delta 2, sorry, yes, thanks. And this here would be delta 1. And this here is also like isomorphic to delta 2, but it's of course just a shift. And so now if I write the K delta in general, this is given as the module A delta, and then I'll, yeah, so I have to say something about this. So I take the codimension 1 cells, so the cells codimension 1, so these are these delta 1I, and so on. And so the complex D I of codimension D. So D is the codimension of the ring, or like the dimension or the rank of this lattice M. And so I get here a complex of conic modules. So I didn't explain what these things are. So these are some open conic modules. So this is the span of the M, where M is now somewhere in yeah, some B in this like codimension 1 I cell plus the inner part of the cone intersected with M. So in the example, if I take my conic, so if I look at delta 1, and this looks like this checkerboard, and so my codimension 0 cell is like the red part, and so if I'm inside that red part, I have a delta. Then if I go to the codimension 1 cell, so what are my codimension 1 things? So these are this codimension 1 and this line is codimension 1, and then I have to see what are these like open conic modules, and you can get them by just like taking, so now this is more like analysis, so you're taking a little epsilon vector for one point in this codimension 1 cell, and then you look what type of module do I get here, and outside of the red region, everything's up here with the yellow, so I would get a yellow module for this codimension 1 cell, so I get an A2. And then also for the other codimension 2 cell here, for codimension 1 cell, everything here is also yellow. So I would get, if I put the module that's like in here, I will also get an A2. And then what are the codimension 2 cells? So there is only one codimension 2 cell, which is this point here. And so this is my only codimension 2 cell in this example. And so now what's here? So if you now complete this, so we would be like at this point here. So if I have a little epsilon vector down here, then yeah, so I'll go back into the red region. So I get an A1 here. And so the conic complex for this red A delta is of this form. And yeah, then you just hum A into this, and you see that the projective dimension of the corresponding symbol is precisely the dimension D, so dimension 2 in this case. And
Can I ask a dumb
Yes.
question? In the last part of the complex, when you took the little vector of the vertex, how do you decide that it points to the red region and not like?
so the epsilon vector has to be inside the C, so you just choose it small enough.
Okay.
So, but there is also a possibility. I kind of here it is. Okay, so these are the conic complexes, and how much time do I have? Like not much, I guess.
3 minutes.
3. Oh my god. Okay. So yeah, just to stay with the NCCR, that you get an NCCR precisely if all these conic complexes have the same length. In other words, if every cell has a codimension D cell. But now, so this was like a short version of like how to prove this. But so now I want like to have like 3 minutes on what's happening if you don't look at normal toric varieties, because then things dramatically change. So this is the third part. So what about normal toric rings? So now there's a discussion if I can call them toric rings, because they already mean normal, and so these are usually called affine monoid algebras.
Semigroup.
Yeah, or semi-group rings, or yeah, what do you prefer? And so they're just now, so instead of that I have this nice structure with the cone intersected with the lattice, I just have like any monoid that is contained in the lattice D to the D. And of course you can ask the same question, like if you are in characteristic D. So question is, in characteristic D, is this n r to the 1 over q still a NCR? So does it still have finite global dimension? And so what you will see is that now you still get the direct summons of this r to the 1 over q. You still can like describe them, so the direct summons are rank 1 modules, and again you cannot get them by like just moving the cone. So you're actually like you're shrinking the lattice, and so I'm not writing down explicitly what they are, so you can describe it. So they depend on 2 parameters, namely m over q. This is something that is like in the lattice, and you make the lattice smaller, and the q is like the power of k. So you can still describe them, but the problem is, so one thing in general is now here that R is not in general a direct summand. anymore, and also this L M over Q Q, they depend like what the Q is here. And so this is what we were like, we're going to a more, not any affine monoid algebra. So look at so-called semi-normal toric or affine monoid algebras. And so there you can show that, yeah, this L M over Q Q are still relatively easy to describe. And so I want to finish with an example. Because the question is like, is this still an NCR? And so the easiest example of a semi-normal toric variety is the Whitney umbrella. So example, so Whitney umbrella. This is the monoid algebra that is generated by y, x, y, and x squared. And so here your lattice is again delta C2. But if you look at this at the monoid that you get, so you get all these points here, so you don't have x in there. And so instead of having a cone, you have kind of a lattice with gaps in there. And in this example, if you choose your P and Q nicely, so for P equals 3, for example, you get two L modules, namely R, or you get three, sorry, you get 3 modules, so you get 2 new ones. So you get the ring R itself, okay. Then you get the normalization. So this is just, you fill the whole lattice up in this example. And then you get a new module L, which is also given by points. And okay. So looks very similar, but you just move it to the side. And in this example, we have a new phenomenon appearing. So if you compute and R plus L plus R bar, then you somehow see that the global dimension becomes bigger. So it becomes 3, which is kind of surprising. And so somehow, if you look always for the symbol of the normalization, this seems to like make the dimension jump. All the other ones seem to be very well behaved, but yeah, the normalization seems to be the problem. And so now we're trying to do more examples and like see if this always has finite global dimension, if it's always for 2-dimensional ones, if it's always dimension also 3, or if we also can get like some like more crazy things appearing, or even infinite global dimensions. That's that. Okay, that's all.
I have a question. If I were going to construct a non-commutative resolution of a non-normal toric ring, what goes wrong if I do this? So take my non-normal toric ring and normalize it, and then map that to end R over Q.
So I think in this example, for example, what you get if you normalize it, you just get like the polynomial ring, and so you just get n R of the normalization, which is just the normalization itself.
No, so I'm taking, so let S be a non-normal toric ring.
Yeah.
And let R be its normalization. Its normalization.
Okay.
So S maps to R, that's a finite map.
Yes,
and R maps to end R1 over Q.
yes,
And that does have finite local dimension, because we proved that, because R is normal,
yeah, but
and
it,
that's a finite map to.
yeah,
why
but
is
I
that
mean,
not a
you would
non-commutative?
just get like the
The same resolution works, is
yeah,
what I'm
it's
saying.
like the same resolution, and I mean, you would get the same resolution.
Yeah. So it does have a non-commutative resolution. So you're just checking if this other thing
Yeah, if
is
the
also.
Frobenius push forward gives us a non-commutative resolution. So you
I
could.
mean, they always exist, so it's sort of. I think,
exist.
unless I'm making a mistake.
Yeah, I think that is correct, but we're particularly interested if the Frobenius push forward gives us a.
Actually, it's similar to like what happens in the commutative world, because if you wanna take a resolution of a non-normal, a commutative resolution of a
then you
non-normal,
also,
if the same resolution works, you just normalize first and then. So
yeah,
Makes sense. But you were just checking whether this particular thing is.
yes.
In part because in this example, for you get just the polynomial right again, so it's just boring. And the normalization just gives you.
So do you think that these are resolution, or these do have finite global dimension?
I think they do have finite global dimension, but we have some like discussions what this global dimension should be. So if it's always just like, bounded, like so far all we've had is 3 for the 2-dimensional ones. But I mean, in theory, it could just be like arbitrarily large, depending on like how bad your non-normal monoid is. But yeah, that's
Michel?
Yeah, in common, I mean, in characteristic 0, the toric rings, the differential operators usually are infinite global dimension. So it's a bit strange that.
this is precisely very, this is very
It has
strange.
to do with some non-materiality or something, otherwise you would expect that means.
Yeah, I mean, all these different rings of differential operators, there are non-Euclidean.
Yeah, but otherwise you would expect to be able to lift it, right? I mean.
But.
There must be something that goes wrong.
Yes.
Differential operators don't lift well, we finally understand.
Right?
You said before that you had the global dimension was less than or equal to the dimension plus 1.
Mm-hmm.
Have you actually done any computations of any specific examples? Or is that really hard?
So these are all like non-commutative Noetherian, non-commutative non-Noetherian rings.
So even for the simplest one, you just doing one example is really hard. Okay.
Yeah, I mean, all we have is just like it's just bound, but.
Well, for the endomorphism rings, it's always the dimension of R.
Yeah, so for the endomorphism,
For that, it's just when you take the limit, you lose control.
Yeah.
I have one more comment. You didn't say this, I mean, probably just because you didn't have time, but the whole argument that you said in characteristic P also works in characteristic 0. Because you can kind of do the same thing with 1 over n.
Yes.
And just in case anyone's wondering.
Yeah.
You don't really need characteristic P for that.
Yeah, that's true, yes.
Can't call it Frobenius push forward anymore.
Other questions? Okay, if not, let's thank Eleonore again.